Let's do another fairly simple example of proof by induction. This time we'll want to prove that for all n greater than or equal to 4, we have that 2 to the n is less than or equal to n factorial. Okay, now notice that n factorial, if you've never seen this factorial notation before, it's n times n minus 1 times n minus 2 all the way down through 1. Now notice that this statement is false if n equals 1, because we'll have 2 on the left-hand side and 1 on the right-hand side. It's also false if n equals 2. We have 4 is less than or equal to 2. That's false. If n is 3, we have 8 is less than or equal to 6. That's no good. But as soon as we get to n equals 4, then we have 2 to the 4th, which is 16, and that is less than or equal to 4 times 3 times 2 times 1, which is 24. Okay, so how do we prove for all n greater than or equal to 4, 2 to the n is less than or equal to n factorial? Well, with any proof by induction, we first need to write a predicate, p of n, and in this case it's going to be simply 2 to the n is less than or equal to n factorial. Okay, and what's our base case? Well, our base case is p of 4, because we want to show that for all n greater than or equal to 4, 2 to the n is less than n factorial. Well, what is p for? We just did it. It's that 16 is less than or equal to 24. So that's true. So now this is where the fun begins. We're going to use our inductive hypothesis, that's this predicate here. Inductive hypothesis. Okay, so we're going to show that for all n, p of n implies p of n plus 1. This is what we need to prove, and that will complete the proof by induction. So since we need to show that p of n implies p of n plus 1, the first step is to assume p of n is true. So think of n as some large number. We've assumed that p of n is true, and we need to conclude, given this fact that p of n is true, that p of n plus 1 is true. So we need to prove the p of n plus 1, which is the statement that 2 to the n plus 1 is less than or equal to n plus 1 factorial. Okay, and I guess technically here I should have for all n, we're assuming that n is greater than or equal to 4. As we've shown, it's false if n is 1, 2, or 3. Okay, let me move this up here. So we need to prove 2 to the n plus 1 is less than or equal to n plus 1 factorial. Well, let's rewrite 2 to the n plus 1 as 2 times 2 to the n. Okay, so this is going to be less than or equal to 2 times, and now we're going to apply the inductive hypothesis. We're going to apply the fact that p of n is true. What does p of n say? This is a side note. P of n says that 2 to the n is less than or equal to n factorial. So by using this fact, we know that 2 to the n is less than or equal to n factorial. We can then multiply the right-hand side by n factorial, because this number here, n factorial, is larger than 2 to the n. That's what p of n says, and we assumed that p of n was true. Okay. Well, now on the left-hand side, we're left with 2 to the n plus 1, and it's less than or equal to 2 times n factorial. So we've almost reached the conclusion here. But notice that 2 is less than or equal to n plus 1. Right? So 2 to the n plus 1 is less than or equal to 2 times n factorial, which is less than or equal to, this 2 here is less than or equal to n plus 1, because we said n was at least 4, so n plus 1 is certainly bigger than 2, times n factorial. And now this is n plus 1 factorial. So what we've ended up with is 2 to the n plus 1 is less than or equal to n plus 1 factorial. That's exactly what we needed to prove. That was p of n plus 1. This completes the proof by induction.